So 11.3b is really just a continuation of uh, part A from yesterday, and we're going to be um, looking more at the limit definition of a slope and then introducing this word derivative, which is from calculus. All right, so a real quick one, just a refresher from the previous lesson, 11.3a. So find the slope of the graph of f of x equals negative 2x plus 4 using the limit process. So the big difference is we aren't given a point to find the slope this time. Like it doesn't say find the slope at x equals 4 or anything like that. It's just find the slope. And the reason in this problem why we don't have to worry about that is because it's already a linear function. So we know that the slope anywhere on that line is the same, and the slope is just going to be negative 2. But this idea of finding the slope using the limit process still applies. So remember that the limit process is limit as h goes to 0 of f of x plus h minus f of x all over h, which we said was the difference quotient in the previous lesson. All we're going to do is we're going to apply that, but without plugging a point in, so x is going to stay x. So what that means is we have the limit as h goes to 0 of, well, f of x plus h is going to plug in x plus h for my variable, so it's negative 2 times x plus h plus 4 minus negative 2 times x plus 4 all over h. And then we can start to simplify this just like we did in the previous lesson. So limit as h goes to 0 of, when I distribute that negative 2, I get negative 2x minus 2h plus 4. I'm going to distribute while I'm kind of simplifying the inside, so it's plus 4x minus 4 all over h. We've said before that everything should cancel out appropriately. Oh, I don't know where I got a 4x from. It should have been a 2x. And now those cancel. So I'm left with the limit as h goes to 0 of negative 2h over h. And those h's cancel. So I get the limit as h goes to 0 of negative 2. And there is no place to plug in an h. And that's so we just have a constant function. And one of the properties from limits before was that the limit of a constant is just constant, so it's negative 2, which we already knew, but we use the limit process to get there. Alright, so for example 2, just find the formula for the slope of the graph of f of x equals x squared plus 1, and then find the slopes at the points negative 1, 2, and 2, 5. So we could just start by plugging in negative 1 and 2 for our difference quotient separately like we did in 11.1a, but since I have to do it twice, it makes a lot more sense to plug the difference quotient on the general function, just like we did on the previous example, and then plug that value into plug our x values in, so we can find slopes at multiple points on the graph without having to do the difference quotient multiple times. So the way that would look is find the limit as h goes to 0 of x plus h squared plus 1 minus x squared plus 1 all over h. So this is identical to what we did on the previous example where we left x as x, then plug in a value. I'm going to simplify. So limit as h goes to 0. I'm going to expand out this binomial. So I get x squared plus 2xh plus h squared plus 1 minus x squared minus 1 all over h. Let's see, my x squares cancel, my 1's cancel. I'm left with the limit as h goes to 0 of 2xh plus h squared all over h. I see that 1h cancels from each part. I'll put the limit as h goes to 0 of 2x plus h. Now I can apply direct substitution because there's no undefined parts. When h goes to 0, I'm left with a general function of 2x. So that's the general equation for slope of any tangent to f of x. So now I can substitute in, I can find the slope at x equals -1, which is -2. And separately, the slope at x equals 2 is going to be 2 times 2, which is 4. So I was able to apply the difference quotient one time here, get a general equation for the slope of any tangent f of x, and then plug in specific x values to that. So once again, we're going to find the formula for the slope of the graph of f of x equals 3 over x, and then find the slope at points 3, 1, and 6, 1 half. So I'm going to start by applying the difference quotient. Limit is h equals to 0 of 3 over x plus h, so that's my f of x plus h, minus f of x all over h. I'm going to get common denominator by part. So f is equal to 0 of 3x minus 3 times x plus h all over x minus x plus h. And that is all over h. Simplify the top. Limit is h equals to 0 of 3x minus 3x minus h over x times x plus h all over h. The 3x's cancel. We get the limit is h goes to 0, negative 3h over x times x plus h all over h. Now those h's cancel, and I'm left with the limit as h goes to 0 of negative 3 over x times x plus h. Now I can use direct substitution. When I do that, h goes to 0. I'm left with negative 3 over squared. So that is my general equation for slope of a tangent to f of x at any point. Now I can evaluate it. So now slope at x equals 3. So we get negative 3 over 3 squared is going to be -3, which is third. So my slope at x equals 3 is -1/3. And my slope at x equals 6 is going to be -3 over 6 squared, which is -3 over 36, which is -1/12. So it turns out that that limit process that we just did to find the general equation of the slope of a graph at any point is called the derivative. So the derivative is just the process to find the slope of a tangent line at any point on a curve. And the way we find that is exactly what we just did. We're going to talk about the notation, but f prime of x, that's how we read that. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And that is like the number one part of calculus, is finding derivatives of functions. And that's just found by using that limit process. So there's different notations we can use. Number one, we have f prime of x is the most common. We also have d over dx, which still means this is just like change in x. Think of d as like the delta symbol. We can have dy over dx if we're talking about a specific function. And there's some other ones too. These are like the main ones, the main notations. This is the number one that we're going to use right here. And again, this f prime of x. Alright, so for this one, find the derivative of f of x that's equal to 3x squared minus 2x. So we don't have to evaluate it anywhere. We're just going to find the general equation for the slope for any point on the curve of 3x squared minus 2x. We're going to start with the limit process. Limit as h goes to 0. Now we're going to be a little bit careful because we have to plug in twice. So we've got 3 times x plus h squared minus 2 times x plus h. That takes care of my f of x plus h minus 3x squared minus 2x. There's my f of x all over h. Start to simplify this down. Limit as h goes to 0 of 3 times x squared plus 2xh plus h squared minus 2x minus 2h minus 3x squared plus 2x all over h. Going to distribute that 3. So I've got 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 3x squared plus 2x all over h. And this is where it becomes important, what I had told you before in class, which was everything from the f of x part should cancel out. And we see that 3x squared, negative 3x squared, negative 2x, positive 2x, and I'm left with the limit as h goes to 0, 6xh plus 3h squared minus 2h all over h. And now everything has an h, so I'm left with the limit as h goes to 0 of 6x plus 3h minus 2. Now I can use direct substitution. When h goes to 0, this whole term goes to 0, so I'm left with my derivative, f prime of x is equal to 6x minus 2. And that is the equation for the slope of the tangent line to any point on that function. So if I want to know where the slope was at positive 4, I could plug a positive 4 into this equation. If I wanted the slope at negative 1/2, I could plug a negative 1/2 into 6x minus 2, and it would give me the slope of the tangent line at any point. Alright, and then one more. Find f prime of x, or find the derivative of x for f of x is equal to radical x. So again, we're going to start with the limit process. So the limit as h goes to 0 of radical x plus h minus radical x all over h. We're going to apply the conjugate, so radical x plus h plus radical x over radical x plus h plus radical x, and I had to do that because I can't directly substitute yet. So I'm going to get the limit as h goes to 0 of x plus h minus x all over h times radical x plus h plus radical x. And now these x's are going to cancel, so I've got the limit as h goes to 0 of h over h times radical x plus h plus radical x. Now I can use, I can cancel out those h's. Limit as h goes to 0 of 1 over radical x plus h plus radical x. Now I can evaluate using plugging in 0. So direct substitution, if h goes to 0, I get 1 over radical x plus radical x, which is 1 over 2 radical x. And that is my derivative of my original function radical x.